Hello again. Let's start with the second use case, oncology use case, for biomarker and biomarker result table generation from oncology nodes. Let's remember the problem. Oncology researchers needs to create a biomarker and biomarker result table, but just from the sections specifically related to the biomarker in the clinical notes. Okay, so here are the steps. We will just classify the sentences, all sentences, to check if they are related to the biomarker or not, because some of the biomarker terms can be with the same writing with the usual words. Okay, so we need to check if it is biomarker or not first. After that, we will extract the biomarker and biomarker result entities from the classified sentences, then check their relationships. Okay, we will create all-in-one pipeline here to handle all these problems with a single pipeline. Okay, first we have documenter again. After that, we split the sentences and tokenize them. After the tokenization stage, we classify the sentences with the word sequence classifier biomarker model, which can return if the sentences are related. It returns and labels those sentences as one. If they are not related to the biomarker, it labels as 0. Okay. After that, we don't need to do any mid-stage processing. We just filter the documents with the document filter by classifier and just filter the are related to biomarker. Okay, sentences that after that we tokenize, we vectorize the tokens, all the tokens, and feed them to the NER model and get the NER model predictions. Like this can return the biomarker results, and then biomarker and biomarker results entities, and we convert them to chunk and check their relationships. We need the perceptron model and dependency parser models, and we used here RE oncology biomarker result, which is trained for checking the relationships between the biomarkers and biomarker results. Okay, we set the relation pair here and then create the pipeline. On a sample node here, we just fit and transform the data. Here is the sample node. And then, as you may see, these are the classification model results, biomarker results, sentence result, and the prediction result means the classification model prediction. These are the, and then when we filter the ones that are related to the biomarker, all of them are 1, and extract the entities from just only those sentences. And here is the table, entity table, relation extraction table we have, as you can see, and some of them are all labeled. All means other, by the way. If they are in a relationship, like biomarker result terms and the biomarker terms are in a relationship, is finding O, it will be labeled, okay? If they are not, it will be labeled as O. Since we have just the pandas table here, when we filter out the O labels, we just have the biomarker and biomarker result table. As you can see, we just use the NLP pipeline, all the NLP models that we have, by extracting the information from unstructured data, from this unstructured data to make it a tabular data for decision making or for research or for other goals, actually. Okay, this is the oncology use case. Let's complete it and go over the de-identification. By the way, all the presentations are shared with the chat box, I guess, here, and also the support team. After the trainings, we will share all the resources with you by email, okay? And de-identification. So de-identification is a really crucial task. And before going over that, let's go over the agenda. After the short introduction, I will explain a case study one of our customers have, and then share some benchmarks and resources. Then we will go over coding, okay? Why we need the identification? It is super crucial task because of the patient privacy, because of several reasons actually. Like for the patient privacy is ethical and legal obligation, right? So we cannot use the patient information openly actually. Like we cannot make it open source, or we cannot share their data, their informations, right? There are some strict regulations over there. And for the data security is another reason. By removing the PHI data, the risk of the data breaches and the unauthorized access is significantly reduced, right? This helps to keep the private data from the wrong hands. So, and also we can, after the de-identification process, we can anonymize the data, right? By replacing the PHI datasets with the fake ones, we can anonymize it. In this way, we can share this after the anonymized data. We can share it with the third parties, right? We can use it with the research or make some analysis on it. You can share it with the other departments or other third-party companies after the anonymization. Okay, there are several compliance with regulations. As you may know, many countries have strict data privacy rules. Like in USA, the HIPAA rules, and also for Europe, there is GDPR, and also the other countries have their own data privacy rules, which regulates the legal penalties, which are can be ended with a prison or large amount of money actually. So if we go over the use cases, this is one of the biggest, the identification use case, actually, Providence. That was presented in our NLP summit, and they used the healthcare NLP library to de-identify 700 millions of patient notes. Okay, and it was completely unstructured data, like clinical notes or OCR, like from the image or PDF files. Okay, and they used in their use case, they used a safe harbor method for the unstructured data and masked it masked it accordingly, and they were able to de-identify 99% of the data, which is actually sounds like incredible. Okay, and they did this by using the healthcare NLP library tools. We have not only the English, we have some other language. We support some other languages for de-identification, like German, French, Spanish, Italian, and Portuguese. You can see the F1 scores of each labels that we have for these languages. So we have also the pre-trained pipelines and the NER models to achieve those tasks. Also, we use, of course, the some other rule-based components like regex matchers, like context-aware rule-based approach like text matchers, context parsers. All these components are used, and we create pre-trained pipelines with which you can use it with a single line of code. Here are the de-identification benchmarks that we got from the other cloud providers. You can check these benchmarks on this notebook also. And as you can see, healthcare NLP library beats in many of them, the other ones. How we solve the problem of de-identification tasks? First of all, as I mentioned in the oncology use case, we need to extract the PHI information, PHI entities first, right? We need to extract the names, dates, age information, or locations, right? So after extracting the entities by using the NER models, since we need to have a robust NER pipeline, we merge those entities according to their performances by prioritization. Okay, and then we feed those merged entities to the de-identification annotator, and the de-identification annotator can return mask the PHI entities, detect the PHI entities, or can replace them with the fake ones, which we say obfuscate. Okay. Here are the pre-trained pipelines and NER pipelines that we have. As you can see, there are several pre-trained pipelines which are trained, prepared with several components, different components, and they can be used according to your needs. Some of them are optimized, for example, which are much more faster than the other ones. Some of them are prepared with the lightweight NER models, okay? And like for also the other language, as you can see. And these are the NER models that we use in the de-identification tasks. All these are for English, and then these are for the other languages, okay? This is the result that we have at the end of the day. Like we have the document and we split it into sentences, and these are the masked results, and it can also return the PHI entities by replacing them with the same length charts. I mean, we used here star. The patient, its length of the PHI entity, it replaces all of them with the star here, as you can see, like 2 here, 25. Okay. If you don't want to do that, you can also do it with stricting like fixed length charts. Okay, when we set it at 4, it replaces PHI entities with 4 star. Also, it can replace the detected PHI entities with fake ones. As you can see, like patient name was replaced with a fake one, and the date, also the age, also the zip code, etc. Okay. Yeah, we also have de-identification demos. You can find any demo. You can find the demos of any models that we have, by the way, on our model sub page. So I strongly suggest you to check that. Also, you can see the different language demos. This is another tool that we have. This is the identification tool. You can see it in our model sub page. You can just paste your text here. I will show an example, by the way, like free text option. You can just paste your text. Please do not use real PHI data, okay? And then it processes and returns the masked version here, like all the PHI entities were replaced with the masked one, as you can see. And also, when you click on the obfuscated text, it is the obfuscated version, okay? Replaced with the fake ones. Also, in the de-identification, in the de-identification tool, the PDF files can be processed, as you can see. Like we can draw black bands over the PHI entities, okay? And then, or like the DICOM images can be processed and can be de-identified like this. Let's go over the resources again. Like you can see the benchmarks with the other cloud providers in this blog post, by the way. The blog post is prepared by our team lead, Veysel Kocaman. And you can see the benchmarks here. And also here is the demo page. And when we go over this one, here is the tool, the identification tool. So this is the de-identified version of it. And when we write here, the patient is 25 years old, female. Since the gender is not PHI, we do not replace it, but it is also doable, okay? Please keep in mind. And her name is Sandra William. Let's test it. Oh, yeah. Here is the age and the patient, okay? Since it is patient, the name is detected as patient, and this is the obfuscated version of it, okay? Okay, let's go over the code, how we do this, how we handle the de-identification tasks. Where is the notebook? I'm gonna show you right here. This is our workshop repo, okay? And you can find all the notebooks that we cover during these sessions in this repo, by the way. So in this session, we will go over the de-identification, clinical de-identification notebook. You can click on here, and there's an opening Colab. When you click on this, you will see the notebook, okay? So we install some libraries that we need to use and start the Spark session. As you can see here, import some libraries and then some information that I already provide you. So this is the de-identification pipeline. So, and here, like several, as I mentioned, we have several NER models, okay? When you click on one of them, like this one, you can see the details here, and you can see what kind of entities this model can extract, okay? Like, for example, this one can do this, and this one is the granular version of it, as you can see. Like, while the generic one can label the names, all the names as name, but the sub-entity model can label the names as doctor or patient, okay? Or the address or the location entities can be country, can be labeled as country, zip, phone, etc. Okay? So after that, we need the PHI entities first, right? As I explained before. So we need a robust pipeline. Since the de-identification task is a crucial one, and we don't want to miss any entity, right? If even though the false positives are actually, we would like to prefer, we prefer that having the false positives instead of missing one of the PHI entity, right? So you can add any NER models in your pipeline to have a robust one. Okay, just let's start with a single one here. I will show how we merge. I already showed it, but I will repeat it again here. Like here are the label descriptions, and this is the PHI data. And then this is the NER model output with the BIO tags, NER model output. But when we convert it as a chunk by using the chunk converter here, its output is the chunks, right? Date, name, ID, age, location, contact information are already extracted, okay? You can also exclude some of the entities by whitelisting or blacklisting, okay? And if you whitelist, you will include. If you blacklist, you will exclude, okay? Here is the all labels that this model can extract in the previous pipeline, but this is the whitelisted one. We remove the location and contact information here, right? How we mask and offset the data, we use de-identification tool for this, okay? Just this annotation does all the work, okay? After extracting the entities, this annotator handles all the de-identification stuff, okay? Here, we set the mode as mask, okay? And since it is mask, it will return masked version of the PHI entities, okay? Also, please note that we set the return entity mappings as true. I will explain why we did this later, okay? This is default as false, as far as I remember, okay? So these are the results after transforming the data, and here are the masked version of the PHI entities, okay? NER model detects the PHI, and then the identification handles to replace them with the masked version or same length charts, fixed length charts, or the obfuscated, okay? We have pipeline output parser component, which helps us to get which helps us to prettify the results easily. Especially this is useful for the products, real-time products also. It returns the light pipeline output as a prettified version. Okay, you can see here with just a few line of codes instead of having large functions or large amount of codes. So as I explained before, there are 4 options for the masking. There are 4 policies actually. Like the first one is masking, and second one is entity labels. Entity labels is already, as I explained, is the default masking policy. Okay, the second one is same length charts masking policy, and the third one is fixed length charts. Also, you can mention how many charts that you will use, okay, here. So these are the outputs, okay. The mapping column, when we set the return mapping column true, it returns the mappings of the original entities, okay. Like original entity outputs are the begin and end indices, because when we replace the David Hale, for example, with a fake one, like Michael O'Reilly, for example, their lengths are not the same, right? So the begin and end indices will be changed. Sometimes the customers need to map them or re-identify the de-identified data sets, so they can they need this information, okay? Or just for checking if they are correct or not, they need this sometimes, okay? For the re-identification, we use this aux column again. Aux column means the mapping column. When we set it as true here, like set return entity mapping says true, when we set it, it returns these mappings, okay? Also, we can use this information, these mappings, and we can re-identify the de-identified data. This is the original text, and this is the re-identified text, okay? So using multiple NER models in the same pipeline, we used the generic one here and used some labels from the generic one, removed the contact and location from here, and used the country, city, hospital, state, street, zip information, which are the location, okay, which are the granular version of the location entity. And we didn't use the contact information here. So we merged their results. We prioritize the NER subentity chunk. If the chunks are detected by the both NER models, okay, in the output, when we set the chunk merger approach here, as you can see here, if they are in the same length, the left one will be prioritized. Okay. For example, the subentity model, if the subentity model labels the Koch Baptist Hospital as a hospital, okay, and Koch Baptist Hospital is labeled as location by the generic model. If we write the subentity to the left side, it will be labeled as hospital. If we change their places, the output will be location. Okay, so this is why you need to check the chunk merge approach annotator and its capabilities for the prioritization. And this will also help us while making the obfuscation, right? If the entity is granular, like for example, the city entity, like New York, okay? And in the fake list of the location label, maybe like a hospital, right? When we obfuscate it, it may be understood. So this is why you need to check the prioritization, okay? You need to spend some attention over here. And when we feed the de-identification, these chunks to the de-identification annotator, we set it as mask here and ignore regex. We ignore regex. I will explain what the regex means here. And here are the outputs, okay? These are the entities coming from the subentity model, and these are the entities coming from the generic model, and these are the merged chunks, final chunk. Okay, here are the results. Like, as you can see, the contact information is missed because why? We didn't include the contact information in none of the NER models. Okay, also we set the regex as true, ignore regex as true. If we set it false, there is some embedded regex rules in the de-identification annotator, okay? In case of the NER models miss some entities, like this one, for example, although we set the contact in our whitelist, for example, the model may miss it, right, as a false negative. Okay, but how we can handle this? The de-identification annotator is strength with the internal regex rules inside. Okay, when we set the set regex override as false, the NER model's outputs will be prioritized. But if we set it as true, if the NER model misses some entities, the regex rules in the de-identification can extract those entities, okay? Not to miss it, okay? Like here, we can also provide some external regex rules in case of the NER models or the de-identification miss some entities that we can define with regex rules, okay? We can provide it as externally here, and we can give the prioritization to the regex. As you can see in the output, the numbers that fits our regex rule are labeled as the number. Okay, we mentioned the labels here. After that, like here, you can include or exclude these. The embedded regex rules are just for these entities, by the way, okay, which can be represented by using the regex rules. Just these entities can be extracted with the de-identification annotator, okay? The other ones can be extracted with all the other components like contextual parsers, text matchers, regex matchers, or NER models in the NER pipeline stage, okay? But if you don't want to see some of them, don't want to enable the de-identification regex rule for some of them, you can just blacklist, and then it will completely blacklist those entities. Okay, like here, it misses. What is the obfuscation and how it works? We created a sample obfuscation file here. Okay, we can feed this obfuscation, your obfuscation faker list externally, like for these labels, like doctor label, it will be used these doctor entities. Okay, these fake names will be used for patient entities. Okay, randomly, and then after creating the NER pipeline, set mode as obfuscate and obfuscate date also as true. We have a parameter for this, like for using the external files, like set obfuscate ref file here. We mentioned the file here. And if we set the obfuscate reference as both, it uses our file and also its own faker list. But the default is faker. If we don't set anything here, as you can see, it will use its faker list, its own faker list, okay? As you can see here, the date has been changed and the David Hale has been replaced with the fake one, Hendrix Nora, also the ID number, the date, and the hospital, as you can see, the street information. So if we set the obfuscation file here and the resource as file, it just used our obfuscation file. As you can see, Khaled Kohler. This is the medical doctor, David Hale. It was replaced with the one of the doctor label, right? Doctor labeled faker list. The faker mode is the default one. It uses only its faker list inside, okay? So if we want to have the obfuscated version of the results, but also if we want to have the masked labels in the metadata, not as a result, okay? Because for having both of them at the same time, we need to define two different de-identification components in the same pipeline, right? With the first one will be obfuscate and the second one will be mask, right? Instead of having this, because if we are working with a large amount of data set, adding the new states may slow down the pipeline runtime, right? Instead of having this issue, we can just remove this and want the de-identification annotator, from the de-identification annotator to return the entity labels in the metadata, okay? So in this way, with a single de-identification annotator stage, we can have both of them, okay? This is the de-identified version of it, and this is the masked version of it. In the output, it returns in the metadata. The entity labels returned in the metadata of the de-identification output, okay? As you can see here. You can also use the light pipeline, which is super useful for the real-time applications. And for the age group issue, and this is an issue actually, because the NER model extract the entity and the identification replace it with fake one. There is no any recognition of the age groups, right? But we have parameters for this. If you would like to have the obfuscate versions in the range of these ages, okay, like 1 to 4, 4 to 12, 12 to 20, 20 to 40, 40 to 60, and 60 to 80. In these intervals, like for example, the 65 will be replaced with the with this interval, okay, with 63 or 75, okay. We can also do that with this ability, okay. Like here, 1-year-old baby, it is replaced with the 3, and 4-year-old kids, it is replaced with 11. When we check the list here, it also fits, right? These are the formal age groups actually, like infant and toddler, child, teen, adult, adult, and middle-aged adult, and senior adults, okay? Age ranges by HIPAA, we have a parameter here. As you may know, if a patient is higher than the 90 years old, it should be obfuscated according to the HIPAA privacy rules. If it is less than 90, you don't have to replace it, okay? You don't have to obfuscate it. But if it is larger than 90, since it is a significant person, a specific person, you need to obfuscate it, okay? When we set the HIPAA age range by HIPAA parameter here, as you can see, none of the age informations has been replaced, but the ones over than the 90 are replaced with fake ones, okay? Name chunk obfuscator approach, you can check this by yourself, and this helps to improve the accuracy of the name obfuscation, okay? And for the date shifting, we support this also. Like for example, you may want to shift the days with a strict number, right? Like or I mean, you can shift the dates with 35 days, okay? All the dates will be shifted 35 days. Also, you can shift the dates according to the specific columns in the dataset. Like we have some patient IDs in the clinical notes, okay? Let's assume that. For specific patients, we have the same clinical notes, right? Like for example, in 100 clinical notes, some of the patients may come to the hospital more than one time. So we have those, we have specific patient IDs for those patients, right? If we want to shift the days according to the patient ID column, we can do that, okay? Like here, there's a document hash coder, and it shifts the days, and then the de-identification, use shift days as true and set region, because the date format can be varied according to the region, right? When we set it US, it will be replaced with it will be shifts according to the US format of the days, okay? Like -5, it has been -5 days. -5, 9, 29, 29. Because why? Why they are the same? Because we use the same patient ID here. Okay, like specific values is another example here. You can create a random number list or with a number list here, and then obfuscate it accordingly, according to these specific column. If the dates if the dates cannot be normalized, okay, like for example here, we know this is date, but we cannot normalize it to replace it with to shift it with a number, or to keep the consistency. Okay, to handle that issue, we set unnormalized date mode as obfuscation. When we set this, if we wouldn't set this, by the way, the results will be just masked. But this can be understood. This data has been anonymized, right, by the third parties. Instead of having this issue, when we set obfuscation, it will obfuscate it with a random date in the faker list. Okay. Multimodal de-identification is also possible. Like if you would like to have obfuscate the, if you would like to obfuscate the phone numbers and mask the entity labels for the ID entities and skip the dates, just skip the dates, and same length charts for names and fixed length charts for zip and location. This is possible. Okay, as you can see, all the combined version of the output is here. Okay, we just set parameters and play with the de-identification annotator parameters and have this. As you may know, the year entities, if they don't have any month information or the day information, the single year entities, it doesn't have to be de-identified, so we can leave them as they are. But the NER models can extract them as date, right? If you would like to leave them as they are, we can create a contextual parser as we did here, like for the year entities, and then create a NER pipeline with these all components, like with the also by adding the contextual parser we have. And after that, we merge the chunks, and 2 times with firstly we merge the chunks, and we merge the chunks of the year entity and the generic model, and then we added the sub-entity model here and merged their results by whitelisting the year entity. And then in the outputs, as you can see, if there is a date information with the year, like here, month with year, they were replaced with the entity label. But here, in the 8, 9, here, 2009, it is not obfuscated, right? Also here. So you can leave some entities if you don't want to have in the output. Unusual pattern usage. If these NER models, for example, some of the dates are extracted, some of the test results extracted as dates, okay, according to our one of our complaints coming from the customer. They had an issue with the NER models that are that extracts the test entities, test result entities as dates because of their formats. Okay, like here, for example, like here, these looks like dates, right? So for handling this issue, we create a contextual parser for extraction of the test results, okay, and then create the NER pipeline here. As you can see, there is no de-identification for now, and all after extracting all the entities like test results, dates here, they look similar, and then we created a JSON file, okay, with the labels, obfuscate the date entities, skip the test results, as you can see, When we feed that JSON to the de-identification model, it returns the obfuscated version of the data entities while leaving the test result entities as they are. Okay? For the structured documents, we have the structured de-identification annotator. Okay, you can just mention the columns that you would like to obfuscate them with the fake ones, and then it can replace it with the fake ones. Okay. There are also like seeds or like faker references. If you have already a specific data set for replacing with fake ones, you can also provide it. Pre-trained pipelines, which are super useful for checking the performance of the healthcare NLP library on your clinical data, like this one with a single line of code. It can be loaded instead of creating the NER pipeline yourself, a large pipeline as I showed, and playing with the parameters. You can just use this pre-trained pipeline, okay, and check the performance of it. If you would like to use it, you can just use it. If you don't want to, or if you want to improve it, we can try to help you for having a better one, okay? But its output in the multimode de-identification pipeline output, since it is multimode output, it returns 4 different outputs, okay, like masked with chars, fixed chars, and obfuscated. But this one is the optimized version, and then it returns just the masked and the obfuscated versions, okay? Also, you can use these pre-trained pipeline outputs with the pipeline tracer and the pipeline output parser to prettify the results, like here. Okay. Thank you so much for listening, for joining today. I know it was a long day. I hope you to see tomorrow again. And thank you so much. See you.